Hello, my name is Dr. Thomas Swift, and this is a sneak peek of one of the modules I teach to our master's students on materials characterization. Okay, so you've all managed to call out a selection of different materials on this street. It's apparent to all of us that everything is made of one type of synthetic material or another. We're absolutely surrounded by it in the world around us. But we can't just take these materials for granted. The reason we use them is because of their utility and their function, and that comes very specifically both from the fundamental chemistry, but the way they arrange themselves. And you all know this, it's something inherent that you've probably picked up since you were a child, assuming you've ever done the washing up. We've all got different forms of clothing, and the majority of the clothing that we wear tends to come from one or two sources. Maybe it's cotton, maybe it's polyester. Now, depending on how much you spend on your clothing and where you buy it from and who manufactures it, you might have a different ratio between the naturally produced cotton or the synthetically made polyester. But, these are two different fundamental, they're polymer chains, they're long macromolecules, and depending on how you use them, you have to wash them differently. Some clothing is quite robust. You can put it in a washing machine at a very high temperature and at a high spin rate, and it will come out absolutely fine. Other clothing is quite fragile. It's going to shrink, it's going to contract, it's going to colour fade. There's all sorts of stuff that can go wrong with it. And that is, in its essence, what material science is all about. It's about understanding that relationship between the material functionality, the cellulose and the polyester. How are they the same? How are they different? And how does that affect how your material actually behave in the macro world, in what you and I can touch and feel? Here are some slides, some pictures I was given courtesy of Croda Europe. They showed me the materials that they manufacture, that they sell to clothing manufacturers to put into your liquid detergents. And the idea here, these are chemicals that coat your jeans and your clothing. Now here's a zoomed in on some denim. The fabric consists of lots of different fibres that are all hooked together and woven into this solid sheet. And the more times you wash it, if you take a pair of jeans and you wash them 10 times, what we perceive as the clothing fading and getting old and getting a bit damaged is actually those individual fibres starting to unwrap, to unknit, them to start to degrade. We have a form here of erosion. And the chemicals that Croda produces, they're sold, they're put into the washing machine with these things, and they make them more robust, they make them more rigid. And that means in the washing machine, there are less fragmentation patterns. There are less points where the jeans can actually start to degrade. That's images taken with an optical microscope. If we go in with a scanning electron microscope, we can see this damage at an even higher resolution level. We can start to try and characterize on the molecular level what's really going on here. Of course, jeans are just one example. Pretty much everything, we wash, that we come into contact with, that we rub, anything that experiences some kind of abrasion will undergo similar processes. So we've also got some comparison shots here of pillow protectors. And again, with the scanning electron microscope, you can see the fragmentation. To you and I, a worn mattress or a sheet is just a piece of fabric that's lost it. But on the nano level, zooming in with a really heavy microscope to see what's really going on in there, what we can see is this assortment of fibres that have begun to become disordered. They were previously well arranged, well overlapped. They gave their strength and their function came from the architecture, from the way they were arranging around each other. But this middle column here, these ones that have been through the washing process without these extra chemicals to give them strength, to give them rigidity, to help protect them, you can see how they are becoming unwoven. Now, chemists in the room will be familiar with this term. It's the introduction of entropy. My goal in this module is to help you form that relationship between size, structure and function, and look at how it's not all just the fundamental chemistry, it's not the functional groups that affect the world and the materials around us, it's all of it combined. And you need to be able to understand the different characterization techniques that can help us unpick this. If I'm going to teach you about material science, I really want to go back to one of the first, I found historical cases of where we really needed material science to solve a problem. And I want to introduce you to natural rubber. This is a material that's harvested from the rubber trees. They are stretchy, strong, waterproof. They've got a bit of a problem. They've got a very low temperature resistance. But in the ancient world, they were primarily found in South America. And from that continent, exports began in earnest to the rest of the world in the early 19th century. It's a really fantastic material. Because of its waterproofing, when they began harvesting it and sending it around the world, it got taken to places like Western Europe, where it was used in coach building. So with the rise of the Industrial Revolution, we began to have people wanting to travel around the country. And before the rise of the automobile, this was traditionally done in horse-drawn carriages. If you'd have to spend days or weeks in the back of this carriage and it was raining and you're carriage was made of wood, the machine would start to mould, it would start to sweat, it would have been quite unpleasant. So they would be searching for different things. You couldn't really use metal. If you use metal to line these carriages, they'd be incredibly heavy and need lots and lots of horses to pull them. Very expensive. And in the modern world, that means more fuel consumption. So rubber, light, waterproof, but not very heavy. You can line your coaches with it, and then you can travel quite easily with relative comfort. The problem with this is, as I said, it's got low temperature resistance. So Western Europe, very cold in the winter, this rubber would sort of contract and break and crack, and you'd lose your waterproofing. Natural rubber itself is the structure of natural rubber. It's a polymer. It's cis-1,4-polyisoprene, and it usually contains about 5% of other additives. We call them plasticizers or surfactants. These are proteins, fatty acids, salts, other things that interrupt this repeated structure. But typically you've got a very, very large molecular weight polymer from 100,000 to 1,000,000 grams per mole. That's very large, lots of repeat units. And because of the structuring of this chemical form, these double bonds will stack against each other. It's not crystalline, it's definitely amorphous, but it has some crystalline properties, and so it forms what we would call an elastomer. For the physicists in the room, this is a low Young's modulus material with a high failure strain. Essentially, it means it's stretchy, you can pull on it, and that is what made it very useful. But when it gets cold in these coaches in winter, the elastomer property is responsive to temperature and humidity. If you heat it up or cool it down, the amount you can stretch it changes. And this is particularly a problem for natural rubber if you let it get cold. It becomes either glassy or crystalline. It loses its elasticity. It becomes very hard. And the opposite direction, heat it up too much, it melts and becomes sticky. You'll get rubber debris sort of rubbing off on anything it comes into contact with. Now, the coach builders of the age, they realised that, they can mix other chemicals into it. They can add other things, and that will change its properties. The hunt was on to try and find something you could add to natural rubber that would improve its temperature robustness, to stop it melting or contracting or freezing or cracking when it was heated up or cooled down, either in the heights of summer or the depths of winter. And this was mass money because it was costing them a lot to scrub and scratch all of the rubber off their coaches every summer and winter to essentially refit the whole fleet every year. If the rubber was more resistant, it would last for longer. Essentially, this is a very early form of trying to move away from single-use plastics back in the 19th century. And allow me to introduce in the United Kingdom a man called Thomas Hancock. You may not have heard of him, but you may have heard of his company, because a few years later, after this event that we're going to talk about today, he merged his company with Charles Mackintosh, who's still with us today. You may have heard of Mackintosh raincoats, one of the most famous anorak suppliers in the world. So waterproof clothing, waterproof, rigidity against temperature. These are very common themes that are still important today. And Thomas Hancock invented, back in the 19th century, a machine to shred waste rubber and allow it to be recycled. This was one of the first plastics recycling plants in the world. And he was doing it purely for commercial means. He was fed up of spending so much money on his coach horses. And so he employed people to do a lot of work on this. And in 1843, in England, patented the vulcanization of rubber using sulfur. Simultaneously, on the other side of the world, in the United States, was a man called Charles Goodyear. Now, you may think you've heard of Goodyear because of the Goodyear Tire and Rubber Company, but that was set up in 1898, inspired by Charles Goodyear. Unlike Mackintosh, which actually does directly come from Thomas Hancock's work, there was no relationship directly between Charles Goodyear and the Goodyear Tire Company because Charles Goodyear died in debtor's prison long before he made any money from this. He was a self-taught chemist and an engineer. He'd spent a lot of his spare time studying rubber, understood how it worked, and he'd learned that sulfur made natural rubber lose its properties back in 1834. So he spent a good decade working on this problem, trying to experiment to improve the properties, trying to get the solution just right. And in 1843, almost simultaneously to Thomas Hancock, he patented in the United States the process for the vulcanization of rubber using sulfur. 2 patents from 2 very different people from very different backgrounds, existing in 2 different countries with a lot of overlap between them. The lawyers were called in to investigate. They were shown a process. They were shown the problem. Both of them were tackling the same problem independently. Both of them were trying to introduce sulfur to undergo this process of vulcanization. The problem is, back in the 19th century, there just wasn't the understanding of what either man was doing to actually explain what was really going on. What they were both doing was mixing sulfur and white lead with the natural rubber before processing, which produced this sticky white material. Chemically, we now know that that's the introduction of these sulfur bonds, which form either interpolymer, so that means they go across one point to another point in the same polymer chain, or intrapolymer, so they link the two different strands together. Think back to those strands, those scanning electron microscope. I said to you, everything's made of fibers. Those fibers, it's the interactions between them, the cross-linking, the weaving that gives these denims, these plastics, these fabrics, their structure. If you can actually draw links between them, if you can bind them together, you reduce their flexibility. You reduce their freedom of movement. They can't unwind, they can't unwrap, they can't unravel if you bind them together. So the sulfur forms these cross-linkers, and then if you heat it, you prevent the independent motion of the chains. Materials up close, polymers are a great example of how at the micro scale, most materials are not the flat, solid, stable surfaces we imagine them to be. And the scanning electron microscope is one way of getting up close to them, but there are so many more that we're going to discuss in these modules. And that's going to be a key theme of these modules. If you were presented a problem like this, if you were called in as an analytical scientist to testify and the case between Goodyear and Hancock, if it was being carried out today, what characterization techniques would you bring in to look at what one scientist and the other scientist had done? How would you try and unpick this to work out who was really copying who? Are the processes that the two people patented the same, or are they subtly different? Is there any infringement of intellectual property here? By the end of this module, I'd like you to be able to answer all of those questions and so many more we haven't even got around to asking yet.